Pleasure.
It's my pleasure.
It's a pleasure to be here this afternoon. And I am going to talk today about a very important topic. The topic is carbon dioxide in the atmosphere. And probably you are well aware that the carbon dioxide in the atmosphere has gone up to some level that probably we have reached level that we're not on Earth for the last probably 2 or 3 million years. As said, 2 or 3 million years. I want to be sure that you get that point, yes. And so and we will see global warming is a direct effect of building up CO2 in the atmosphere. There's no doubt about it. And it's changed the globe temperature, but also the ocean temperature, which have major issues in terms of ice melting, ice sheets melting, but also sea ice melting. Also the coral reefs, which is a topic that I've been working on for quite some time, almost my entire life. Coral reefs don't do well when it's getting too warm. They bleach, and I'm going to show that to you at some point as well. And also if you add too much CO2 in the atmosphere, you change the pH of the ocean, in the upper part of the ocean, which is not a good thing either for any organism trying to produce calcium carbonate in their test. I don't know if you have ever seen this picture. This picture is very special. You were not born yet. And it's a picture, the first time a human eye could see planet Earth, from passing the moon. It's even before, the human being, went on the moon. It was a year before, and it was, this amazing view of our planet there, yes. It's a very interesting planet. It's a very special one, and it's mostly a great planet because we have water, yes. Probably you've never seen our planet that way, yes, because it's often not really shown, because it's amazing to realize that, the Pacific Ocean, covers about half of the planet. Have you ever thought of the planet that way? It's not too surprising that we call our planet the blue planet or the blue marble. And water is very important. The ocean covers 71% of the Earth's surface, and it contains almost the entire water on Earth, 97% of the entire Earth water. So oceans are very important. Water is extremely important for the evolution of life on our planet. It's almost impossible to have life on any other planets unless you have some water. If you see this is our planet as well. And what do we see here in our planet? We see how much we have changed it, yes. We can see that at night, we can illuminate the planet. We do illuminate the planet, yes. You can even, if you don't see it very well, this is North America, you can see that we have changed dramatically, our planet Earth. Well, to the level that it's very dark, and it's really, now extremely, lighted there. But if you think about, us Homo sapiens, having, changed the planet so much we can light it up at night, this needs a large amount of energy, and, this society that we have developed based, on oil and gas, fossil fuel burning, has some major, consequences. Here, a quote by Rosby in 1956 already. He says, tampering can be dangerous. Nature can be vengeful. We should have a great deal of respect for the planet on which we live. We have only one planet. It's our spaceship, and there's very little places or no places to go, at least for a mass, exodus, if our planet is not going to be habitable anymore. This is I decided to show you the face of Professor Rosby, and so he looked at the large scales, in the 30s, 40s, 50s, large scales of circulation kind of in the atmosphere and in the ocean. There's Rosby waves, probably some of you might have read this in your introductory book, are on his, a name on his honor, yes. And, he was born and raised in Sweden and came to the US and ended up, being a professor at the University of Chicago. Okay, so I didn't introduce myself too much, but I want to be sure that you know that I was born and raised in Switzerland. And Switzerland is not Sweden. Okay? How many of you will be confused? But often when I introduce myself, born and raised in Switzerland, I came here in 1978, so I'm a full American, fully Americanized, full American citizen, but also I've been in Texas for 30 years, at Rice University. And I feel that now, at least my colleagues and friends in Texas think I am now a Texas citizen after 30 years, even though I don't really speak like one, yes. But anyway, it has been a pleasure for me to be, to live here in Houston. I've raised my family here, and I'm still kicking, even though I'm not as young as you guys are. So if you see this picture here, this is the atmosphere. Our planet is very special because we have an atmosphere. Some other planets have different types of atmosphere. But this atmosphere is extremely thin. As a matter of fact, when you go and look at this, you might see the stratification of the atmosphere. Yes, you can see this yellowish orangey color, and after you see this black colors there. This is the top of the troposphere. When you fly, most of you I'm sure have flown, you fly at about 30,000 feet or maybe 40,000 feet now with the new planes. You will be flying just above the clouds there. Yes. You will be, just above, on the top of the troposphere. This planet is special, and it has also an amazing, atmosphere, which is very thin, and we need, to take care of it. Here, is what we have in this atmosphere in terms of gas. Yes, we have mostly, nitrogen. We have, thanks God, oxygen. There's some argon, and this tiny little bit, of carbon dioxide or CO2. When you look at it, it's 0.038%. Small amount. But this, CO2 concentration in the atmosphere is, extremely important. If we had no CO2 or water vapor or methane in the atmosphere, the temperature, on Earth would be 15 degrees cooler. So it's good to have these, what we call greenhouse gases, yes. So without them, the planet Earth would not be habitable. So even though we have this really small amount, so what, and quickly here, this is, this energy balance, from this, obviously, our energy, comes from the sun. And so it comes, in shortwave radiation. So this shortwave radiation can go mostly through the atmosphere and be reflected and be absorbed by clouds. And some of it will be absorbed on the surface of the Earth. So these are, the units are watts energy per square meters. So 340 watts per square meters arrive on the upper part of the atmosphere. Only 161 would come and be absorbed on the surface of the Earth. And here, this solar, will be absorbed, within the clouds, within the upper atmosphere. And 100 of these, are going to be reflected by the surface of the Earth, in particular when you have, white surface like the desert or snow and ice. Now the Earth is being warmed up, but at much lower temperature than the sun, and now it's re-radiating, not in short wavelengths, but in large wavelengths in infrared. And now this infrared re-radiation by the Earth can be absorbed by these greenhouse gases. And that's the important things. These greenhouse gases will capture some of this re-radiated energy from the Earth at the infrared invisible wavelength. And of some of it is going to go and escape to space, yes? So if you want the Earth to remain at the same temperature, like your bank account, what comes in and comes out should be equal, yes, if you want to have the same amount of money on your bank account. But here, so you can see kind of this 340 minus 100, that's what comes out right away kind of from this shortwave radiation. So it's 240 watts per square meters. Here, now, with what we have added on in terms of greenhouse gases in the past 100 years, now we have 239. Meaning that kind of we are capturing, because of this increase of greenhouse gases, we have now, kind of capture, kind of some of the heat longer into our system, and the Earth is warming. There's no doubt about this. Arrhenius, kind of in the late 1800s, already had warned the idea of burning fossil fuel would increase CO2 in the atmosphere and would, kind of warm up, the globe. Okay, so where is this CO2 come from? Kind of all of us, and I came here, by car. I'm guilty as anyone. Yes, we live, in this society where we are completely dependent, almost completely dependent on fossil fuels. And so, kind of when you burn your gas, what you do, you oxidize it, kind of with oxygen. And now the byproduct is, first, you can drive your car, you can fly your plane. Yes, you get energy out of this, and you can, but kind of the byproduct is H2O, water, but also carbon dioxide. And that's kind of the bad side of using fossil fuel, because we are increasing the carbon dioxide in our system by burning fossil fuel. So if you think about kind of just the other way around, yes, photosynthesis, carbon dioxide, water, some nutrients, phosphate, nitrate, the sun, the energy, and now you can create a glucose, one of these organic tissue that is, kind of a large part of our life, and you create oxygen. So this is just the opposite of what we do when we burn fossil fuel, yes? This will be, kind of turn into, some different types of molecule of gas or oil or even coal. So when you do oxidize this, you get out, some energy, and you produce CO2 in your system, yes. So, I don't know, probably most of you kind of understand what kind of fossil fuels are about, yes. So very long time ago, kind of you have production, of plankton, sea life, algae, microbes. And these, in areas where you have very high productivity, you can really create, through photosynthesis, large amount of organic matter. This organic matter would accumulate on the seafloor and will be buried, especially if these waters are devoid of oxygen, so there's no oxidation. So now you accumulate on this large organic material, so you are drawing down CO2 to produce, kind of these large organic tissues. If these organic tissues are not recycled, automatically, kind of now you're taking this out for millions of years. They are buried deep enough to change the temperature and pressure, and now this organic matter is turned into fuel, yes, into fossil fuel, oil, gas, and coal. And what do? We are using this fossil fuel that we're accumulating, for a long period of time. We now kind of use this and oxidize it, burn it, and we use this, as a source of energy to light up the Earth, to transport ourselves, to have this wonderful life that we have, kind of here on our planet. So, kind of just here, so this is gas, petroleum, and coal, ethanol, kind of. So, if you burn, gas, you produce, this is energy content, about 51, kilojoule per gram. If you, kind of use petroleum, you get a bit less, 43. If you get coal, much less, 39. And this release, kind of the amount of CO2. So, for burning, gas, you get a large amount of energy and you don't produce as much CO2. On the other hand, coal, you produce less energy and you emit more CO2. Reason why, it's much better to burn, natural gas than to burn coal. And we have plenty of both at the moment. Okay, so here, I think I can put this in motion. I thought I did. Doesn't look like it. Up. Oh, for some reason, I thought it would be, but so this is, it's an animation, but it doesn't want me to do any animation at the moment. But what you have, here, these colors here, this carbon dioxide concentration in part per million. Yes, you remember, it's 0.038%, so part per million. And so you can see, where do we have the most production of CO2, on Earth? It's in the northern hemisphere. That's most of the people live. Most of the southern hemisphere is just water. And you can see, North America produce a large amount of CO2. Europe does as well. And also here, the Far East, China in particular. Okay, so this is where the CO2 is produced mostly today. But because it's produced and is emitted in the atmosphere is extremely dynamic. So this CO2 is going to be transported everywhere. So by burning fossil fuel in one area is the issue and a problem on a global scale, yes, because it's going to be completely mixed up, through the entire atmosphere. And we will see this. Okay, so there are wonderful, websites. You can go to NOAA, the National Oceanographic and Atmospheric Administration, a federal, administration, very important. Whatever forecast you can have on weather is mostly or only based on data collected by NOAA. And so the federal government has done marvel to give us access to this amazing amount of data. One of the data they do on an hourly basis on top of Mauna Loa, which is the main island in Hawaii, they measure carbon dioxide in the atmosphere. You would say, why Hawaii? Well, it started to be done, in the late 50s, and by Dr. Kipling from the Oceanographic Institution of Scripps. He went up there, because it would be away from the major industrial center. And so we will see, now we have a wonderful record of the atmospheric, CO2 concentration measured in the atmosphere since the late 1950s. But this is, and I just downloaded this just this morning or yesterday. So this is, 2017. This is January 9th. This is February 6th, 2 days ago, 3 days ago. And so, all these points, are hourly average and daily average, are there. So, how on February 7, this is the concentration of the atmosphere in CO2, 406, part per million. You can see, it does vary a little bit, through the days, but not very, very much, yes. Okay. You can go now instead of just looking at a few days, you can go now here, this is January. And so this is a full year there. And after February and March, yes. So this is, from February 2017, this is where we are there. And you can see, this is, the part per million, 408. And you can see that, yes, CO2 goes up, reach a maximum in May. This is also Mauna Loa, and goes down to a low, sometimes in September, and start to grow again. So the CO2 in the atmosphere is not just growing, steadily, but it's also influenced on a seasonal basis. And so I wish I could ask you a question about this, why that is, yes?
Yeah.
Yes.
Why?
But do you know? Because I thought you should know. But if you don't know, it's really interesting. It's how, kind of the Earth is breathing, how the biosphere is breathing, yes? So CO2, and you could hear, from some people, CO2 is important, because more CO2, the plants are happier, yes? They grow faster to a certain level. But so what happened here? So when you are here, in September, what happened in the Northern Hemisphere in September? Most of the biosphere on continent is on the Northern Hemisphere, yes? So what has happened in September? Fall. Very good. And so fall means, kind of the biosphere is going to slow down, even stop growing, yes? Leaves are going to die, leaves are going to decay, and now so the trees and the grass and everything, the biosphere on the continent is not going to be active, so it's not going to take CO2 to grow. But it's also going to decay partially, so now you're increasing CO2 in the atmosphere. At the end of the winter, in May, now you have reached, kind of a high concentration, kind of in this case 408. And what happened in the summer? Well, between May, and September is the time, when the biosphere is fully active in the Northern Hemisphere and now kind of capture some of this CO2 to create, kind of this organic tissues, yes, through photosynthesis. So says we do have, kind of about, kind of, if you think of 408 and 401, about 7 parts per million seasonal variation of CO2 in the atmosphere. And so if we go kind of further back in time, from 2012, you can see this beautiful, kind of seasonal cycle. But on the other hand, if you take an average of all these cycles, kind of these lows or these highs are never at the same level. They increase every year. Yes? So, for instance, kind of this low, kind of there, at the end of 2016 is, at about, kind of 400 and let's say, kind of 1.5. On the other hand, this low here, at the end of 2012, was at 391, yes. This is what we are emitting by burning fossil fuel, this increase, of CO2 in the atmosphere. If you go, kind of to the very beginning of the measurements, late 50s, you can see, kind of this beautiful seasonal cycle, but you can see also in the black line here, the average that we have started on kind of at about, kind of 318, kind of in 1958, and now we are here past 400. And this is steadily, it's not even steadily, it's increasing. The rate of increase, kind of is higher and higher. And I don't know if you can see this. From me here, it's a little bit washed out, but you see the blue bars there? So this will be, kind of the annual mean growth rate of CO2 at Mauna Loa. And so these are part per million per year. It's a rate, yes? So you can see, kind of in the early years, we had, per year, 1 part per million increase. And for this, kind of doing this, kind of the 70s, the 80s, the 90s, kind of from 20 to 2010, now we are looking at 2, part per million per year. And now we will probably going, to 3 in this coming decade. So there's a steady increase of the amount of emission of CO2 in the atmosphere. Okay, so you are stuck, if you want to measure, kind of the atmospheric, CO2 concentration, directly by instrument. We don't know anything else beside past, beyond, the late 1950s. Scientists are very clever. They went and drilled, kind of some of these, kind of ice sheets in Antarctica. For instance, kind of low dome and dome C. And so what they found out, if you drill, kind of ice, and they've drilled the entire ice sheets, 3.5 kilometers, takes at least a decade to do this. They realize when they take, kind of this ice, kind of it's not just purely ice, but there are air bubbles trapped in the ice. And so clever glaciologists were able to measure atmospheric gases trapped in the ice back in time. Is that clever? Amazing. I have to say, these are a French group from Grenoble and also some Swiss physicists, from Bern, University of Bern. They did this in 1980s. The red kind of data there, this is measured in the atmosphere since the late 50s. Here we go now to 1,000 years, kind of before present. All of this are measured CO2 in the air bubbles in ice cores. Okay? Wow. So, when you look at this, you say, okay, in the last 1,000 years, CO2 was about 280 parts per million, and sometimes about 1850, we started to add CO2 in the atmosphere. And from 280, we have reached 400. So, well, is that unusual? It's kind of unusual, especially when you look at cores that were drilled, kind of first at Vostok and Dome C or Epica, where you can go now through the entire ice sheets and you can measure, kind of CO2 down, kind of this core, looking at the bubbles of air. So here we are. This is 2012. This is our measured, kind of CO2 from the 1950s. This is our low dome, kind of there. And after this, it's going back, whoa. We can go back 800,000 years. And what do we see? Well, kind of the measured CO2, and this was just a big revolution when we were able to, kind of really go back as far back as 800,000 years, and realize that every time it's cold, for instance, this cold event here, 20,000 years ago, it's called the last glacial maximum. The Earth was 5 degrees Celsius in average colder than today. Chicago was under more than 1 kilometer of ice. Huge ice sheets in the northern hemisphere. So the Earth went from, some cold event like this, where we had, kind of a CO2 of about 185 parts per million. This a warm period there, like we have, kind of today, prior to the Industrial Revolution. The numbers are about 280 parts per million, so about 100, kind of ppm difference. And after this, this amazing increase, yes? 1979, 336, January 2012, 393, and today, 400. So, what's the conclusion here? We have had never on Earth, a 400 part per million CO2 concentration, at least in the last 800,000 years. So we are, kind of creating an amazing, we are running an amazing experiment. Now, in no time, we are increasing CO2 by more than 100 parts per million, in less than 150 years. So the rate is absolutely fabulous. You can go back, even further back in time, yes? Now here, we're talking about geology, yes? 800,000 years is barely geology. But, kind of now here, this is today. And now we are going back, about, kind of 65 million years ago. And now we have no ice record to measure, kind of CO2 in the atmosphere. But we have ways of doing it. I cannot really go into the details, but it's not as precise as measuring, kind of air, atmospheric air trapped in ice. But we have methods. For instance, kind of about, kind of 50 million years ago, we estimate that CO2 would have been, about 2,000 parts per million. The Earth was very, very different, 50 million years ago. Crocodiles were living, kind of in a high latitude of the Arctic. We had absolutely no ice on Earth, no ice sheets whatsoever. So high CO2, much warmer Earth, and kind of the entire kind of Arctic Ocean was subtropical. And at some point, and I cannot go into the details, the CO2 start to decrease. And sometimes, at about 34 million years ago, this is when the Antarctic ice sheet started to grow. So there's a good connection between CO2 decrease in the atmosphere and, making an Earth like we know today. So here, kind of we had, a CO2, if you believe this, at about slightly higher than what we have today, about 500 parts per million. That's when we started, kind of to have, kind of the Antarctic ice sheet. If you go, kind of now, sometimes around here, there's another drop of CO2. And there's, interesting enough, when you drop sea level below 350, it's the time, when the northern hemisphere ice sheets start to grow, kind of in North America and Siberia and so on. So there's a good connection between ice sheets formation and CO2 in the atmosphere. And now, as we mentioned, we have reached 400 in 150 years, just to give you kind of a context within this. All right. So CO2, kind of carbon dioxide is the main greenhouse gases, but we do have methane. There's also kind of some nitrate and some other types of greenhouse gases that we are producing ourselves. And this, kind of explain, kind of this amazing, kind of increase, of energy we are keeping into, kind of the Earth system. And so by, trapping, by this greenhouse blanket that we are creating, by emitting and burning fossil fuel, now kind of the Earth is trapping this energy, mostly, kind of in the ocean. 93% of this entire energy, extra energy, is trapped in the ocean. The ocean are becoming warmer and warmer every decade. And this heat can be kept in the ocean. And sometimes, like we just, kind of witnessed this, when we have what we call an El Nino, part of this heat is now transferred back to the atmosphere and warms up, kind of the Earth tremendously, as it happened in 2016. So this is what happened. This is all of these data are from, this is from NASA. So we have this amazing data set. And so this is from 1888, from 20, probably, kind of 16, yes. And so this is a temperature anomaly. So what it is, if you take an average, of all of this data and look, kind of if you are above the average or below the average. So this is, kind of everything is above this, and you can see, kind of this continuous, kind of increase, of temperature, kind of on a global scale, yes? And so we are looking, at about 1 degree Celsius increase in the past, kind of century on a global scale. So, I don't know if I can play this. Oh, yes, I can. So this, I'm going to show you, kind of how the Earth has increased its temperature, kind of since late 1800. So this is, kind of -2 in blue and 2 degrees Celsius, above, kind of this average. So we are now in the 60s, the 80s, the 90s, kind of, and now. So this was last year. Yeah, but this is a very interesting, kind of point, here. At least visually, if you didn't believe, kind of this rising, kind of temperature, kind of on a graph, it gives you a sense, kind of. Obviously, the warming is not everywhere at the same level. Even some areas, can some light slightly, kind of on the cooler side, yes. But overall, and what's the overall? Where do we have the most, increase of temperature? In a well, where people live, but not really. Where the polar bear live, yes, but mostly, kind of in the high latitude, of the northern hemisphere. It's unbelievable. Even today, I don't know if you have looked at the news. This winter is unbelievably different in the Arctic. Today, probably, kind of the temperature in the North Pole is at 0 Celsius or 32. It's even sometimes above freezing, which is something that nobody has ever seen. So things is happening. Okay, so not only, kind of, as I said, the land is warming up faster, but the ocean is also warming up, yes. And the ocean is not warming up as fast because you can draw down this energy and keep it in the water for some time. So if you see, kind of here, this is from 1880 to 2013. The orange curve is temperature. This is CO2. There's a good, correlation. I could spend a lot of time on trying to explain to you and convince you that yes, there's a direct connection between burning fossil fuel as we do in our societies and the increase of temperature that we have, witnessed. There's no doubt about this. And there's a place like this, kind of the 10 hottest years all since 1998. And if you think about, from 2010, we have 2014, 2015, and 2016 were kind of the warmest, kind of year ever recorded since the late 1800s. Okay, you can see the same thing. 2016 was unbelievable. Probably kind of all of you have read this because it was all over the news. But you can see that kind of from January to December 2016, the temperature was always above the previous one, 2015, which was also an unusual warm year. Okay, so this kind of temperature, and I cannot go through this. So what are the consequences? Well, kind of now it's in September 2012. This is sea ice extent in the Arctic. The yellow would be a regular, average September sea ice cover. In 2012, you can see this was one of the minimum sea ice extent in the Arctic. And the beauty, kind of now, some people always kind of use this, yes? Well, transport. You can go kind of now from Rotterdam, and you can go all the way through the Arctic, and you can go to Tokyo instead of going through the Panama Canal, for 2 or 3 months a year, and you save 30% of energy by going through the northern route. So we have even passageway now coming, kind of opening up, kind of in the Arctic at that time. This is even more spectacular in a way. This is kind of Arctic sea ice, and this is from October to February 2017, yes? It's now. And as I mentioned, kind of the Arctic is unusually warm, and it's so unusually warm this winter. The blue curve here, you can see the extent of sea ice during the winter is the lowest ever recorded. Okay, if you look at the monthly Arctic sea ice from January 79 and 2017, you can see kind of this kind of systematic drop of the extent of sea ice. It's sea ice. What about ice sheets? This is a picture very common now on Greenland. On top of the Greenland ice sheet, kind of now more and more kind of ice that is now trapped on continent, on big ice sheets like Greenland, is melting. And kind of what happened kind of when you create kind of this melting of an ice sheet? Well, the water you have from the ice sheet has to go back into the ocean. The rate of sea level rise has increased dramatically in the last century. We are talking about 3.3 millimeters per year. Now it was probably more in the order of 1, before, kind of 1800, yes. Another amazing consequences of this warming is what we call, kind of coral reef bleaching. Coral reefs, kind of today, the most common one, have decided kind of to live in symbiosis with an algae. They lived in very low nutrients environment, so they had to capture, kind of in the juvenile shape, kind of this algae. It's called zooxanthellid, and these algae produce the food, kind of for them to grow. And so they were able to capture, and live in this very low nutrients environments, low latitude, high temperature, and because of this association, they are very picky. They don't like it when it's cold, like all of us. 18 degrees Celsius as the boundary, kind of for the lowest temperature. We didn't realize that 29 degrees Celsius was probably the highest temperature they could cope up with, at least kind of the current one. If it goes higher than 39, it has happened, they decide under stress to release kind of their zooxanthellid, and now they have no way kind of to use these zooxanthellid for food. And if this happened long enough, they bleach, and if they bleach long enough, they die. And kind of this, you also probably saw this, the Great Barrier Reef has had some major kind of issues in the past year. And this is this amazing reef. The Great Barrier Reef is 2,500 kilometers long. It's an amazing animal, because these reefs, these corals are polyps, millions and billions of polyps. So 2,500 kilometers here, kind of this is 1998, a major El Nino, 2002, some kind of a small El Nino. This is the 2016 El Nino. And you can see kind of there, the northern part of the Great Barrier Reef, you had 81% severely bleached. Amazingly, amount of bleaching, at that time. And this bleaching, we knew it from the 1900s, but you can see, kind of this bleaching becomes more and more common because the Earth is getting warmer and warmer. And this is probably the last one. almost the last one. Another situation here, if you bring CO2 in the atmosphere high, you increase, and this is kind of also kind of close by kind of Hawaii, and you can see kind of the pH kind of the ocean is, so the CO2 in the ocean, kind of in blue, is also increasing, and now in green, the pH is decreasing, and it's decreased by about 0.1 unit of pH, which is 30% increase of acidification. It's not acidific. It's not acid yet, thanks God. But this also creates some major issues for any organism producing calcium carbonate. All right, I love this picture. I was probably your age, kind of when I saw it first, probably a bit younger. But this is, kind of 1968. And at the time, when you would be, kind of at that age, you wanted to be a scientist. I wanted to be an astronaut. Swiss astronaut is not that easy, but I realized that, kind of the ocean can give you, this amazing location where you can discover things. And that's the reason why I became, a scientist, but mostly a marine geologist. And I cannot remember, I need kind of to remind you again of this amazing quote by Wasby: tampering can be dangerous, tampering the planet. Nature can be vengeful. We should have a great deal of respect for this planet. We have only one. And if we are changing kind of the Earth climate so much, we might have some major issues kind of in the near future. Thank you very much.